we move on to the next topic, next part, which is how can we use the full adder to perform binary addition of two binary numbers which is more than 1 bit in size. Let's say, for example, take this example, will be three bits in size. Let's use a specific example. Let's say you are trying to add 011 to 111. So 011, let's add to 111. Okay, now let's try to do a manual addition first. So 1 plus 1, answer is 2, right? 2. So it's 0, it's a 1. So of course in addition we don't put a 1 here. If there's a carry, so carry to the next stage here. Excuse me. Now 1 plus 1 plus 1, answer is a 3. So 1 represents 3. Similarly, we carry over to the next stage of the addition. 1, and then so the next stage, 1 plus 0 plus 1, answer is 2. 2 is represented with 1 0. So in this case, there's no more bits to add, so we just leave the 1 as it is there. Okay, so the answer is 1010. Now let's take a look how we can do this addition using a full adder. So these are my full adders. In using a full adder to perform this addition, you must focus on one column at a time. So I want you to look at this column and this column and this column. Okay, now so let's look at the first column, which is handled by this full adder. Okay, in this first column we are trying to add 1 plus 1. This is the rightmost column. There's no carry in, so you can imagine there's an imaginary 0 here. Okay, so in fact what you're doing here is, so this is your A, this is your B, this is your C in. Okay, so is A is 1, B is 1. Your C in, we set it to a 0 because this is the first stage of the addition. So 1 plus 1 plus 0 refer to the truth table that we worked out just now. Assuming your circuit is designed correctly, it will produce the correct result. 1 plus 1 plus 0 is 2. 2 means answer is 1 0. 2. Sum is 0, carry out is 1. Now let's add the second column. 1 plus 1. The second column will be handled by this full adder. Okay, 1 plus 1. So your A is a 1. A is a 1. Okay, your B is a 1. Now your carry in, okay, is actually a 1. And where do you get the carry in? Look at the manual addition. We're actually getting our carry in from the carry out of the previous stage. Okay, so there's a 1 here and we carry it over. So there's a 1 here and we are carrying it over. So we are literally connecting the carry out of the first full adder to the carry in of the second full adder. So since it's electrically connected, if you have a 1 here, and you'll be getting a 1 here. Okay, then let's try to work out what is the answer. So based on our understanding of the truth table, 1 plus 1 plus 1, that is a 3. A 3 is represented as 1 1 in binary, and yeah, we are just using the truth table to show the answer. Okay, so it's 1 1. So let's focus our attention now on the third column of the addition. And the third column of addition is implemented using this third full adder. So we're trying to add 0 plus 1. Your A is a 0, B is a 1. So A is a 0, B is a 1. Okay, and where do you get this 1? This in manual addition, you are getting the 1 from the previous stage where it is carried out and goes to the carry in. Okay, of the next stage. So likewise, yes, so in the previous stage you have this a carry out of 1, yeah, just like you got here 1. So we have carry out of 1. So now we are basically connecting this carry out to the carry in of the next stage. And so yes, so in fact what you're trying to do is to add 0 plus 1 plus 1. According to the truth table of the full adder, 0 plus 1 plus 1 is a 2. 2 gives you the answer of 1, 0. Okay, so that effectively, if you connect it this way, you can basically get the result of adding two binary number together, and this binary number is actually 3-bit in size. 3-bit in size. Yeah, can you take a look? It's 3-bit in size. Okay, so let's see if it is correct. So if you were to to make it to make the diagram become, let's ignore this, let's ignore the carry out to carry in, just cancel it away and just look at the sum. Just focus on the sum. The sum is here, so let's look at the sum. Okay, this is our sum. Okay, you got a 0, 0, 1, 0, and the last part is a carry out, just like here. It's a carry out. The last part we use a carry out to represent the number. So you got 1, 0, 1, 0 as the answer. Just like here, you got 1, 0, 1, 0 as the answer. So that is basically how we use a full adder to perform binary addition of two numbers. Okay, so these two numbers is represented here. Your first binary number is your A. Your A is 0, 1, 1. So if I look at your A is 0, your 0 is here, your 1 is represented here, and your 1, 0, 1, 1, that is your A. Your B is represented by 1, 1, 1. Okay, and you can see from here, your 1 is representing your A, B. This 1 is represented here. This 1 is represented here. That is your B. Normally we will, yeah. Okay, and the result, okay, where do you get the result? This is your result. This is your result, 0, 1, 0, 0, 1, 0. And we use the carry out to also represent as part of the result. Now this is the carry out, which we use it to represent the most significant bit of the binary addition. We could also interpret this binary bit here as an overflow bit, because why? When you add 3-bit binary numbers, 3-bit plus 3-bit, potentially you may result in a situation where a 3-bit number cannot be, the result cannot be contained within the 3-bit number. It requires 4-bit to represent the entire addition. And if that being the case, then when addition, like in this example, results in a 4-bit binary number, okay, where if a 1 is flagged out here, it means that the 3-bit binary addition has resulted in an overflow. Alternatively, you can also use this bit coming out from C out as a way to represent the most significant bit of the addition. Okay, the most significant bit of the addition is this. This is the MSB. Likewise, you can use a carry out here to represent the most significant bit of the addition. So I hope this tutorial gives you an illustration how you could add two binary numbers together by connecting full adders in series in a continuous fashion, one after another. So this example shows you how to add a 3-bit binary numbers, two 3-bit binary numbers. Let's say, for example, if you need to add two numbers, and these two numbers is 4-bit in size, then you would have introduced another full adder okay, and you will repeat the way you have connected. A carry out is connected to the carry in of the full adder. and your A and B would be tapping from the next bit, and so on. Your A and your B will be connecting here, and then here you got the sum, you got the C out, and so on. And so if you need to add two 7-bit binary numbers, yeah, then you need 7 full adder, and you connect it in series in this manner. So I hope you enjoyed this video, and I hope you understand how a full adder is used to add binary numbers of any length in size.